the solid states, we can now have some examples of the everyday, because the symmetry operations by themselves are mathematical constructs, and they don't look into account what the symmetry is applied to, meaning structure, atom, whatever. It could be a chair or whatever. So we can start looking for this kind of thing. Okay, let's look objects, what kind of symmetries they have. So okay, banana is an interesting chiral molecule. It's not a molecule, but it only has one-fold rotation, so identity. So you cannot do anything for this because it's a chiral molecule. But then we can have a propeller, like this kind of a propeller. Of course, this has a two-fold rotation. You rotate 180. Or you can have a four-fold rotation propeller, or three-fold rotation propeller, or six-fold rotation propeller. Of course, you can also imagine molecules which have this symmetry operation. So it's okay. You can have a three-fold rotational molecules or four. And this is now how the general coordinates with the six-fold rotational axis is being defined. So it sits there and now is rotated 1, 2, 3, 4, 5, 6 times, starting at one point. And it creates this set of coordinates. So when we have one point fixed, so we know this coordinate, and we know that there is now a six-fold symmetry, which is now marked like this, it will create these 5 other ones. So this is the actual idea what I told you about the benzene ring. So if the benzene ring is sitting on a six-fold symmetry axis, we need to define only one atom. All atoms comes from symmetry. And that helps a lot our work, because the more symmetry is there in the structure, then with the fewer individual definitions we can create the whole thing, meaning the unit contents of the unit cell, meaning contents of the whole crystal. That's the idea. And this definition, this is now a picture on a book or tables called internal tables for crystallography, and this notation is called a space group. A space group is a set of given symmetry operations in a given unit cell. And now I know by heart this because it's a six-fold symmetry. It has to be a hexagonal symmetry, and then P means primitive hexagon. And then the idea is this is the notation for this. The P6 means hexagonal, primitive hexagonal crystal system. It doesn't tell us anything about the unit cell. It doesn't tell the size of the unit cell, but it tells us what is the symmetry operations inside that unit cell. And then we can have a roto-inversion axis, which is the extension for the previous one. So we add the minus there. So we had previously 1 and -1. Now we can have -2, -3, -4, -6. And the roto-inversion is to rotate the point around the axis and then followed by inversion. So this is rotation inversion, and that's the roto-inversion axis. This is what it means. And the idea is that now we do the handed net will change. So we start from here, we rotate like this, and then reflect on or invert to the center. So it goes here. And at the same time, the handedness will change. Now again, rotation 90, we go here. Now reflection on the other, or inversion from through center in here. Now 1 becomes 4. Now we can repeat it. We can repeat it like this. And now, finally, what we have created is 4 positions when we do this. And now we describe as P minus 4. And here the name for this symmetry operations. And here we can see 1 coordinate set creates 3 other ones. And that's the idea. And we define this, name this symmetry accordingly. So in this case now it would be -4, roto-inversion axis. Roto-reflection is in principle the same thing, but now the minus sign has been now substituted by a mirror. But now the mirror, we have to define where the mirror is happening. Of course, we cannot just arbitrarily put the mirror plane in there. We have to define it. And we define it in a certain sense. The roto-reflection is marked like this. So rotation and perpendicular, this means perpendicular to this one, we have a mirror. So rotation and mirror, rotation and mirror. And then we can have here 2, 4, and 6. The reason now why there is not 3 is that it's embedded, it's a minor section of 6. We don't need it. And the product is here. You can see rotation, the axis followed by reflection and mirror respect to the plane normal to it. That's the idea. And then perpendicularity is marked with slash. So the slash means that now it's a combination of two symmetry elements which has a particular orientation towards each other. And we have to agree what it is that we know that we don't lose the reference point. And the point is the first coordinates created by the rotation, and then the mirror comes in there. And now there is an example of that. So we have a twofold rotation and a mirror. So first rotating and then mirroring, one will create 3 others. And this is how it works. Now we have here P. This is called the P2 over M. P here means primitive. And it's primitive, this kind of radius at P2 over M. Now you can see that there's a beta angle here is indicated. So it means it's a monoclinic system. And now it's a monoclinic P2 over M. That it's a special set of symmetry operations in a monoclinic system. Regardless of the size of the unit cell, the shape is now determined. And then we are now moving to the translational elements, which are different now. Because there's a movement, there is translational movement. All the other previous ones didn't include any movements. They were inside the unit cell, reflecting or mirroring, but now there's a movement. And the first one is screw axis, and screw axis is indicated by a subscript 1, 2, 3, 4, and 5. Here we can have 5. Because this is about how it moves. And now what is there is this is coupling translational element of rotation leads to so-called screw axis, which is a helical axis also. The motive is rotated first, divided by the n, whatever the n here is, and then immediately translated m over n distance in the lattice. And here is an example for this. This is a very nice example. So we start from x, y, z position there. And now we rotate, this is a 3-1 axis. So we rotate this 1/3, so 120 degrees there, and then translate 1/3 of the unit cell again. Here we have the axis defined. And now the same sequence, we now 1/3 movement, 1/3 movement. So it's this one, like this. That is how it goes, of course, but if we do this correctly, it's really like a complete movement. But now it's always a fraction of a movement inside the unit cell. And this cannot be, doesn't exist in any other form than in a solid state. And here is the idea, like the 1/3 implies clockwise rotation, 360 divided by 3, followed by translation of 1/3. On the lattice contents direction. So lattice content is the agreed direction. And now if it's in the monoclinic system, then we agree that it's the axis where it goes along. And then the idea is that the initial coordinates will be different. Like in here, this is a 3-fold symmetry, so the general coordinates will now create 2 other coordinates. You don't have to memorize these. Now you can see that this name is P31, which is just an indication about the screw axis. You don't have to know this by heart. You don't even have to read the book which contains these. There is a big book of this thick where all these are listed. These are actually copies of these things, so pictures from this book. Because now they are inside the computer programs. The computer programs know this. But if you look, my first, one of the first slides in the first lecture, there are some links to it. So there's also an electronic version of these international tables where these are listed. So if you're interested in looking, you can find it out. Then finally, the idea is there is Clyde plane. And now, because it goes along the plane, we have to define a plane. So we define it A, B, C, N, or D. This is a little bit more complex definition, but in principle, it's easiest way to describe this kind of a thing. It's like a movement of this. So what you do, you translate, reflect a mirror, translate a mirror, translate mirror, and this is how it goes. This is like this kind of a movement in 2 dimensions. Of course, 3 dimensions is slightly different. And the idea is that this is a little bit complicated thing to do, to visualize again, but here we have now, when we start from the XYZ position, we now glide along the, in this case, C axis, and now at the one half of the length of the axis, then we reflect that on the other side, and that gives the new position. So this is gliding along a plane, a certain plane. Now it's here is defined, the plane, an AC plane, and it goes towards the C direction, and then it's reflected on the other side. And now it's easy to understand why we have so many things in here, because the plane can be also defined as a diagonal plane. Doesn't have to go this, because it's a plane anyway. And that's the idea. So we can have definition. So if we have an A plane, then it moves 1 over A. B, of course, the movement is B over 2, or if it's C, it's that. So it's along the axis. Or it can be diagonal, or in cubic systems also, it can be diagonal. So it goes like but this is only existing in the cubic systems. And the point in here is that this is rather complex to think about, but luckily it's rather rare also. This is on very highly symmetrical structures, you can see this kind of a thing. And the idea is that here, example creates a glide plane through C-axis. It will create y, x, y, z, makes you x minus y half plus z. Because now it has been along the C-axis, so z will be added by 1/2. And now the idea with the n-axis, so it's diagonal for NC plane. Now it is that we add half in 2 of them, because it's along that AC plane. So A and C will have additional increment of 1/2. But these are all possible. This is just descriptors how you can determine the position of the next entity, atom or a molecule. Is there this kind of a possibility? And these are the possibilities we have. So this is now clade plane symmetries. I will just skip it very briefly, but this is the actual idea, and these are the symbols. These are on a very highly symmetrical cases or this kind of a thing. But then this means that more you have these symmetry operations, the more symmetry operations, the more additional coordinates will be created. And the old book, I will also go this very briefly, the old book used graphical notations on the name of the symmetry operations. So that's the idea. So this kind of a thing indicated that it's a 1-2 screw axis. This is easily and understandable 3-fold axis. And these are the those 6-fold axis here, like this. Here, this is an interesting thing. 4 over m is made a sign like this. Nobody is using these anymore. These are not. You have to go in the literature, which is 50, 60, 70 years old when you see these things presented. But that's just the idea that because the theory has been developed 100 years ago. So now our idea here is to identify the symmetry operations, because this is actually what we are doing. So when we have our molecule and we crystallize it, we might know the molecular structure. We know that it's a ibuprofen, for example. We know that it's ibuprofen, but we crystallize it. We don't know how it's organized. So there has to be the other ibuprofen in this direction, the other ibuprofen in this direction, and so on. But it has to be periodically ordered. But luckily, the information what we get from that, so the spots, will tell us this. So that information about the symmetry is also embedded in the information what we get from the instrument. And based on that, we can then identify, okay, yes, there is this kind of a symmetry is there. Then we can assign, yes, now this molecule has this kind of, or the structure has this kind of a symmetry. So now let's see what we have of these symmetries. So now, of course, this is a very simple thing that these, if it's done by hand, like I was doing like this. So it's simultaneous rotation and translation as twofold screw axis. And here, of course, the idea, this is the old measurement, old sign also here. And the idea, if you have this kind of a thing, of course, you have a twofold axis. Now in here, easily understood, we have a center of inversion of -1, because these hands are very good examples. Now in here, of course, this is an exotic looking hand system, but you can see the thumb is always on the same side, so we have a fourfold symmetry there. So one hand creates 3 other hands, and here, of course, logically, 6-fold symmetry. Now in here, that's simple. Also, again, there is a mirror, so we will mirror this in this side, and the right hand becomes the left hand. And then in here, of course, it's also very simple to see that, okay, yes, there is a 3-fold symmetry axis in there. Sometimes it's easy that we know when assume the symmetry in a crystal based on the molecular symmetry of our entity. But sometimes you cannot, and often it's not the same. So you might have that you have a highly symmetrical structure in there, and the molecular symmetry is very high. Let's say something like ferrocene or whatever. But then when it crystallizes, it actually doesn't show any packing symmetry. So they can be the same, but might not be the same. So this is always the idea, is that we have to look for the symmetry of the packing, the symmetry operations inside the crystal, not the molecular symmetry. And this, of course, is glide plane. So then mirror, moving line. So this is how it goes. So this one now is the same as that one, of course. And if we consider that in the unit cell, this is in the unit cell 1 and this is in the next unit cell. But this is one of the most complicated things to realize, is really that we don't have your own target molecule there. We have all the molecules, and they are organized in 3 dimensions. So now when you take all this into account and start looking what is the total picture of this, so we can build up a hierarchy of crystal systems, and then the space group. The space group is just a name for the individual symmetries in a given crystal system. And we had 14 of these crystal systems. Now we develop, okay, what we can have there. So the crystal systems arranged hierarchically. The higher crystal system contains at least one symmetry element of the lower, doesn't contain. So we go like this. So we start from triclinic, we go to monoclinic, and then from the monoclinic we will have orthorhombic and trigonal, which are very similar. Tetragonal is of higher symmetry, and the hexagonal is slightly higher than tetragonal, and the highest is cubic. So that is the hierarchy in that sense. So the point in there is that triclinic type of a symmetry, so identity, can exist in all of them. But now in the monoclinic system, we can have, for example, screw axis, which cannot be on a triclinic system. So that's the idea. But luckily, they are all coined. They're all being done, calculated 100 years ago and tabulated, and now you can find these things in the computer programs. So now the HM notation comes, it's more quite clear in that sense that we have a triclinic system. In a triclinic system, we have only possibilities is 1 and -1, nothing more. Because the symmetry of the unit cell doesn't allow any other symmetry operations. So all these center of inner center of symmetry can be there. Now in monoclinic system, we can have a twofold axis, we can have a mirror, and we can have a combination of these two. We can have 2/m symmetry in there. And these are possibilities what we have in the monoclinic system as point groups. Orthorhombic can have 2 mirrors and a rotation, or we can have, the highest case is that we can have a rotation and mirror in all the axes A, B, and C. And then we can have also a rotation, of course, M222, so twofold rotation of each of these axes. So these are the possibilities of that. But now in tetragonal, we have more possibilities. So we have a fourfold identity or central symmetry, or then we can have a rotor reflection or rotation, mirrors, and the combination of these, we can have them. So you can see that now, in many of the cases, when the symmetry of the unit cell goes higher, the symmetry operations or possibility symmetries are increasing. This is not exactly true in the total numbers. You will see that later on. But that in principle possible. Some of them are, of course, restricted. Trigonal, we have always the threefold symmetries are possible. And the highest can actually be this kind of thing, -3, 2 over m. Symmetry in trigonal system. Hexagonal has, of course, can have all these possibilities, and the highest would be that there is 1 6-fold and 2 2-fold symmetries coupled with mirror. So this is theoretically possible. This has been theoretically calculated, all these possibilities. And cubic can have, of course, the rotations, and then it can have the rotations, 3 rotations in all these axes, or we can have mirrors also on these axes. And this is a very high symmetry. And now, if you now take all these 32 crystallographic point groups, which are possible, and these are now joined together with the possible symmetry elements which can exist in there. So you will come up in a graph like this. So this, in principle, is the same as you saw earlier. So triclinic, monoclinic, trigonal, orthorhombic system is here. This is orthorhombic. There we have a lowest cubic. There we have a tetragonal space group, and here we hexagonal and higher hexagonal. So this is actually the idea of how these different symmetry operations are joined together when you go higher in the unit cell symmetry. So the first thing what we have to do is to determine the unit cell symmetry. What is the crystal system? Is it triclinic, monoclinic, whatever it is? And then we have to look which kind of a symmetry it contains. Because if the unit cell is incorrect or the symmetry is incorrect, then the mathematics doesn't work. So as a result of this combining all the possible things, including translations, with the 14 Pravda lattices and 32 point groups, there is exactly only 230 possible symmetry operations inside these unit cells. So you cannot organize any material on any other way than these 230. And in this case, these are the calculated ones. They're already ready there. Each of them represents certain set of symmetry operations, how the symmetry is being done. Luckily now, there are new crystallographic programs in the diffractometer already, or then afterwards, read the data and looks for these things. They are looking for analyzing the data and seeing, okay, what kind of symmetries would be there. But previously, let's say 50, 60 years ago, you have to do it by hand. From the diffraction images, you have to look, okay, is this real or not? Is there a symmetry or not? And that's the point. So each point group symmetry crystallography describes a periodic repetition of a structural feature from around the point. So that is the idea. So that gives you the idea that, okay, start from here, follow these symmetry operations in all directions in three-dimensional space. And that is, again, a short summary of this. So when you have a crystal system, triclinic, which kind of symmetries you have there? None. And then how many point groups you have, how many space groups you have. Space group is really, each individual space group is a list of possible symmetries or symmetry operations, how the coordinates are changing. And then how many Pravda lattices there are. And that is the idea of the whole coining up this kind of a thing. So I will go briefly. So monoclinic, what there can be is a rotation or mirror. So how many point groups we have? 3 point groups, and makes 13 possible combinations of these things. So there are, in the monoclinic system, 13 possibilities to do this. And we have 2 Pravda lattices. We have a primitive and the centered cell. It's typically the C-centered can be also something else depending, but that's the case. And then orthorhombic, you will have more symmetry operations. You can see here, twofold, a mirror, and we have our 3 point groups, but now we have a 59 possibilities because we have so many Pravda lattices that this is making the idea that we will have so many possibilities. So sometimes in the orthorhombic system, it might be difficult to find the correct one because it has to be one of these 59. And it's the orthorhombic system. The tetragonal, as of course, a fourfold symmetry, it has 7 point groups possible and 68 possible combinations of these symmetry operations. Again, we have to be able to pick up one. And it has 2 Pravda lattices also in this tetragonal. It's the same as in the monoclinic case. Hexagonal is there. We can have it in trigonal and hexagonal. This is like a joint in here. So in trigonal case, we have 5 point group, only 7 space group, and in addition to 18. And then in a hexagonal, when we have a 6-fold rotation, we can have 27. And finally, the cubic, we have 4 times 3-fold rotation, symmetries, 5 point groups, and it makes 36 possibilities. And this is now 32 point groups and 230 space groups. 230 possible ways of organizing material in the 3-dimensional space, periodically ordered. And that's the case. And we have 7 lattice systems in general. This is a short combination. If you are using instrument, you might see these kind of things in there. That the MP means simple, this primitive monoclinic. OP means simple, meaning primitive orthorhombic. OI, body-centered orthorhombic eye, and so on and so on. But again, these are more or less nowadays automatically are outputted by the instrument. But now something more into there. So we have now defined the basics, how to make X-rays, how to make the monochromatic, how the diffraction happens in principle from the imaginary Miller index planes, which is then converted to the reciprocal lattice point, which we can then measure the reflections by a diffractometer. But then these reflections are then influenced by the symmetries inside the unit cells. The reflections also tells us the unit cell and also tells about the symmetry. So the crystal is very important for us in order to be able to determine correct unit cell and correct symmetry operations. And sometimes can be really difficult. Sometimes even okay, the crystal is so bad that you can't get this done. But now we go a little bit deeper in what we see inside the unit cell based on the symmetry. And the point in there is that this is a term which is very useful. It's called an asymmetric unit. And now asymmetric unit is a part of a unit cell which is repeatable. So this is, and concept-wise, the same as unit cell. Remember, unit cell is the smallest repeatable unit where you can take the whole crystal. Asymmetric unit is the smallest possible unit which makes the unit cell. So the unit cell is divided into asymmetric units. And the point in there is now that it's a part of the crystallographic unit cell which can use to generate complete unit cell by symmetry of the space group, symmetry of the unit cell itself. So the symmetry operations are creating the other half. And we call that part an asymmetric unit. And the point here we have a unit cell like that. And in this unit cell, we have 2 molecules. Yeah? And now, if we remember this kind of a thing, we can look for this, that this is the symmetry operation, which indicates here it's P21, so it's a 2-fold screw axis. So now this molecule here is related to this molecule by this symmetry operation. And now the idea is that there is only 2 molecules in the unit cell, and then the idea we have 2 coordinate sets, so coordinate for this and coordinate for that. But now, because we know this symmetry operation, we know the P21, then we don't need the coordinates of this. That we need to know only this part. So we have to determine half of the unit cell. And this part, which is now the white area now here, is called the asymmetric unit. The asymmetric unit is a unit by repeating that you get the whole content. And in this case, this asymmetric unit creates the other half of it because there's only 2 molecules. But you could imagine that there would be 4 molecules in there. And if there would be a symmetry, a 4-fold symmetry, then the asymmetric unit would be 1/4 of the unit cell. So what this means that we don't have to determine all the atoms in the unit cell. We determine only those which are in the asymmetric unit. So it's like splitting the unit cell into smaller parts which are all equal. That is actually the point. And then helps us a lot, of course, because in here, if you count the atoms, how many atoms we have? 15 maybe, the other 15 here. If we would not have information about the symmetry, we would have to determine all 30. But now we know the symmetry, we define only 15. And then the computer program knows automatically this one. So it knows this, so it's showing this. And sometimes this is really a point if you are using first time some computer visualizing program. They might show you by default both of them, or they might show you only the asymmetric unit. That's why I said you might see half of a molecule, because it means that the half of the molecule makes the asymmetric unit, and the other half comes from symmetry. But this is a very useful concept on thinking about what you have in there. And sometimes you have a 1 molecule in asymmetric unit, sometimes you have a 1 molecule and a solvent molecule there, or you might have 2 molecules, some rare cases 3 molecules in an asymmetric unit. But the point in there is that it's just a very good information for us that the symmetry actually inside the unit cell helps it. There is only one example, or one case where this is not true, because in the lowest symmetry, this is P1, this is a triclinic chiral, there is the asymmetric unit is the unit cell is the asymmetric unit, because there is no symmetry. But in all the other cases, like in here, we have asymmetric unit and the other ones come from symmetry. So that's just an indication for this. And now are some simple mathematics which will help you to figure it out. What do you have in your hand? This is really a more practical tool already, that the Z is a number of formula units in the unit cell. So if we have, let's say, ibuprofen, and we now know that there are 4 ibuprofen molecules in the unit cell, it means that the Z equals 4. And this is very useful in the beginning of the structure determination to know this set. Because when we know the symmetry operations, meaning the space group, then it's possible to calculate how big is the asymmetric unit. So what is the amount of atoms you determine there? And this is actually the Z. The Z is actually the number of atoms in an asymmetric unit. And now when you know the Z, it is possible to calculate the density. And this is how it works. So the density is, of course, it's mass divided by volume. So why do we get this? So mass is very simple, because if we know our molecule, or we guess the molecular weight, let's say that it's 100, then we know from the symmetry operations of that unit cell that there should be 4. If you can calculate how many coordinates it gives you, that Z equals 4, then you can multiply, you get the mass, and then when you get this one, the volume is actually Avogadro's constant multiplied by the volume of the unit cell, which you can get from the instrument. So you have all these numbers. This you can guess, and this you should know roughly. And the point in there, that's it, is the multiplicity, how many times the asymmetric unit is repeated, and the formula weight is there. Now, there is an even simpler, but there will be a calculation. You will see how it works in the next slide. But there is an even simpler rule, because you can also assume that the atoms take a certain space. And the idea is that an approximation for a light atom structure is 17 cubic angstroms. And then you can, with a non-hydrogen atom, then you just do it in a by Z. You can calculate volume divided 17 times X, and then X is the number of your atoms there. Then you can create the Z. On the other way around, you can, if you know the volume and you know the Z, you can now estimate how many atoms you have. So always when you have only one unknown, you can then calculate it very simply. You can use also 20, it's not a big deal. So the idea is okay. Calculation with 20 is easier than 17, because you can just multiply it, very simple work. You can even calculate it by your hand. But what this happens in real life, I have a couple of examples to do this. So here, an organic molecule, this rather nice name, I will not read it anyway, but it has a molecular formula of C16, H15, nitrogen O2. So we got it, we crystallized this thing and got the nice crystal, put it in a diffractometer, and the diffractometer tells us, okay, now it has a unit cell of a certain set. So the idea is that the program tells us that it's A, B, C are there, and all angles are 90. So you can see that this is not the same as this, and this is not the same as that, but all the angles are 90, then it's orthorhombic. So this we know. Normally the computer program already tells you, okay, it seems that you have an orthorhombic cell now. And this calculation, it gives you the volume of 2,526. But our data was not very good, and the probability, the program tells you that, okay, you might be only 80% correct with the unit cell, because the data is bad. So if data is excellent, the program tells you, okay, with very high probability, that's correct one. But you can't be sure. But in this case, we are not sure about this. So we can test this thing. That are we okay? Is this really what we have in there? Because sometimes it happens so that you are thinking that you are crystallizing your target molecule, but you are crystallizing a starting material. And the starting material might be different. So this can happen. It happens quite often. So the idea is now the test that whether the cell choice is reasonable for your data collection, meaning this one now here, we can calculate Z. And now there's the calculation. What we do, we take the volume. Now we use 17 angstroms in here. We have 19 non-hydrogen atoms in there. We get, because it's an estimate, we get 7.83, which is 8. Because the Z has this thing that when you look for this, it's always an integer number. It's 1, 2, 3, 4, 6, 8, 9, this kind of a thing. So it always has, it cannot be anything else. So then we know that it's 8. And now when you check the orthorhombic space groups, their multiplicity, meaning the Z, you will find out that it's either 4 or 8. In some cases, it could be also 16 to 18, but that's the idea. So the point in here, Z equals 8, is absolutely fine. So it means that everything what we get, it means that there's one molecule in asymmetric unit. But this is this test that, okay, is our unit cell what it proposes to, is it correct? Can it be correct? Yes. Yet at this point, we cannot tell if we can solve the structure, but we can tell that, okay, it looks to be okay. Because the only thing when we can be absolutely sure everything else once we have done the work. So this is the difference between any other method, that you are unsure of virtually everything until you have done it to completeness. And that's the idea. That's the idea. That's the point. And then the idea is the idea. That turns out to be that that's the case. Our compound is crystalline. It's chiral. This is our space group number, meaning the symmetry operations. This is a chiral. There is no center of symmetry in there. And then it has 2 molecules in asymmetric unit. So actually what we now calculated, this 8 means 1 molecule, but in this case there is actually 8, so it means that we will have 2 times 4 molecules in there. So here you can see the 2 molecules in an asymmetric unit, and now when you multiply this by 4 times, it gives you 8 molecules in the whole unit. And this way we can calculate, when you can estimate, because we know that either 4 or 8 both can be correct. But in this case, it turned out to be that actually our molecular formula was suitable for that, but actually the unit cell is that big that it means that we have to have 8 molecules in there, in the idea. And it comes from this space group. But anyway, that's one example. The other example is this kind of a thing. It's the same thing with the same compound now, exactly the same compound. It can happen. Now we get a different unit cell. Now we get, look, it's definitely smaller. The previous one was 2,500. Now we get 1,800. So what is wrong? Or is there anything wrong? Let's check. Let's calculate the Z here now. And we can now get, and Z says 5.63, which is about 5 or 6. But now, in the previous case, we know it's orthorhombic. It cannot be 6. Now something is wrong. It has to be either 4 or 8. But it cannot be 6. So now, the most orthorhombic space group has this, as we spoke already, 4 or 8, and then the other ones. Now we need to look for this Z times M, and now when we have a Z, we will put one, the Z prime, let's say call it like this, how many atoms we have in the asymmetric unit is 1, it would be 5 or 6, however we round it up. So if we now take 2 in the asymmetric unit, so that the 6 is not enough for us, we have to multiply that by 2. So we will, Z prime means how many molecules there are in the asymmetric unit. Then it will give us 10 or 12. Again, illogical. So both numbers are illogical. So this number and that number is not okay. But we think that our unit cell is correct. What is then wrong? What is there? And this is a very good thing. So the first, either our unit cell is wrong, or my idea about the chemical content is wrong. So either one, it has to be. Either unit cell is correct and my composition is wrong, or the unit cell is incorrect and my composition is wrong, or right. So now that we can play a trick with this, so we can now think, okay, where did it come from? Did I crystallize it from somewhere? What was the solvent? Because we crystallized that from the solvent. Okay, let's think about something. Let's add, for example, solvent molecules. Let's add a toluene in there. We crystallized it from toluene. So could it be so that our molecule is now crystallizing with the toluene? And then the toluene is part of the structure. And we just do this add now. We redo the calculation. Now the only difference is that now into here we add 7. So this number will change now to 26. We repeat this kind of a thing, calculation, and we get 4.11, which is 4. Yes. Now the idea is there that the point is, I'm sorry, the point really is that now we manage to find out that our unit cell is correct, but our chemical composition is not correct. So because it was lacking some atoms. And this way we can, the very simple calculations, we can check that, okay, is this okay? We haven't solved the structure yet. This is just an idea what could be there. But that will tell us, okay, we are on the right track. So we make the correct choices, because if we do incorrect choices, we correct an incorrect unit cell, that's a bad thing, or incorrect symmetry inside the unit cell, that's bad, or we have a badly different composition, that's also bad. So we have to be able to have some kind of a knowledge on this, okay, which kind of a thing is there, which is correct. Because then you might work weeks and you lost all the work because you made a mistake in the beginning. But this is a very nice way of checking for these things. we should stop at 12:30, and now it's 12:27. So it's very nice to stop on time now. And now we are slowly for tomorrow. It's nice that my computer works, as you noticed that I was able to show the simulator program. And if you want, I can send you this. I can give a link to the simulator program. It runs on a Mac. It's an executable file. So you click it, you can open it up, and then you can play around with this. There is no instructions for this, but you can just play around and see how it works. So that's a very nice tool to try to understand this, because then in the next things we will go real into programs, and we do the work here. I will show that in first theoretically, and then I will show you in practice how it works. And then we will go on after this. You will also can do this home if you like. I will send all the data to you, and you can get the programs. So it's nice practice. It's very easy to follow the handouts. Good. Please do this and that and that. But then we move the final stage, or second final stage, is so that we will analyze what we have. And this is a very important thing, because the point is there, I will give some examples. When somebody has published a paper which is completely incorrect, the analysis of the X-ray structure itself is okay, but the analysis of the structure is completely incorrect. It was not what they claim it was, because they had an idea what it should be, and they were forced it to be like this. They were seeing, let's say, with the pink eyes through it, oh, this is what we want, and it turned out to be it was not. So it's very important not only to know what you're doing, but also to be able to analyze everything correctly. And this is a very crucial point. Nowadays, we have a very good instruments. They're very fast, and you can get the data fast. But the idea, the real work starts when you have to analyze. And this is actually where we move on from tomorrow. So, okay, today is done. Thank you very much for this, and we continue tomorrow.
So anyone have any questions for this session?